So we start the second part of this basic course on control systems. In the first part, we have primarily seen modeling, right? In which we actually found models for electrical, mechanical, and electromechanical systems. And we found the models in two domains. We found the models as transfer function models in the S domain, and we found the models as the state space models in the time domain. Now, immediately after modeling, the next step that is uh, evident is analysis. So why do we have the model? We have the model because we want to analyze the system. Mathematically, we model it and then we analyze it. And what is analysis? Analysis is that you have the model of the system, right? You have the system and you subject it to certain input and you are interested in finding out the output, right? So this is the subject of this unit here. So we'll in this part we'll study the time response of different systems and how to characterize the time response, right? Because that will help us in actually framing our control problem in a more mathematically proper way, right? So so suppose we have any transfer function in the S domain given as GS. We subject it to an input RS, and we are interested in finding out not only CS but actually CT. We want to see how is the output behaving with respect to time, because this is what we want to characterize. Because when we have a physical problem of, for example, designing a lift traction system, once we are able to characterize it, only then we can say that our lift would have to behave like this or it is going to behave like this. What is the response of the lift going to be? What it should be actually, right? So in order to do this, we need to first find out how do systems behave with respect to different kind of inputs that we subject them to. As far as inputs are concerned, we already know we have seen the standard inputs that we apply to control in the control system framework. But still, just to go through it, just to revise it slightly more. So these are the seven standard inputs that we generally encounter in the study of time response of control systems. So this is the impulse input, right? In the time domain, it is written as delta t. In the frequency domain as 1. This is the step input. In the time domain, it is written like this, ut. In the S domain, if you take the transfer function, if you take the Laplace transform for the step input, you'll get 1 by S. This is the ramp input. So you have this, let me write this down, impulse, right? This is step, this is ramp, right? This one, and the Laplace transformation would be 1 by S squared. Now this is polynomial input t raised to the power n, right? And the response is going to be n factorial divided by s to the power n plus 1. This is an exponentially decaying input, e to the power minus at ut. You can find out the transfer function 1 by s plus a. This is a sinusoidal input which actually starts at time t is equal to 0. That is why it is multiplied with unit step. All these inputs are multiplied with unit step. So suppose you have a sinusoidal signal which is like this, right? But this sinusoidal signal that you'll apply is actually this sinusoidal signal multiplied with a unit step. So this is the sinusoidal signal that we're talking about, because we are very specific about the time at which we are applying the input. So that is why you have this product sine omega t into u of t. In a similar way, cos omega t into u of t. So these are the important S domain representations of these inputs. So suppose you have any given uh, transfer function. Let me take one transfer function, s plus 2 divided by s plus 5, and I'm applying a step input to this transfer function, right? So so uh, the question is, I know C of S because C of S is just going to be the product of these two but the question is, do I know C of t, right? And I want to know C of t. So the 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 uh, the process of finding C of t is actually the process of finding the time response for this system. So for finding CT, I need to take the inverse Laplace transform of this, and that's a standard thing in that you must have seen before. So CFS is written as A by S plus B by S plus 5, where A and B are unknowns, and it is equated to the right hand side, which is S plus 2 divided by S into S plus 5, and then we can write this as A into S plus 5 plus B into S divided by S into S plus 5, and you can equate these two sides, right? I'm just writing this again so that you remember what you have done in your mathematics courses before. So from this you get two equations. One equation is A would be equal to S plus 2 divided by S plus 5 as S tends to 0, and the other equation would be B is equal to S plus 2 divided by S as S tends to minus 5. So from this you can find A, which is equal to 2 by 5, and B, which is equal to minus, which is equal to 3 by 5 here, which is equal to 3 by 5. So you can write down your CS as 2 by 5 uh, by S plus 3 by 5 by S plus 5, and this one you can take the inverse Laplace transform and write 2 by 5 plus 3 by 5 e to the power minus 5t. So this is the time response of the system in response to the step input. Now you can see that this has two parts, a constant part and a part that is decaying. So this part is similar in nature to the input, because your input is also step and this is also a constant function. So this is similar in nature to the input. Since the input is called the forcing function, this is called the forced response, and this is similar to the particular integral that you do in differential equations. And this has a part which is because of this minus 5 here, and minus 5 is there because of the 5 present in the denominator. So this is something, this is present because of the nature of the system, and that is why it's called the natural response. Natural response. You would notice uh, this is similar to the complementary function that we obtain when we solve for the differential equations. Now you would notice one more thing, and that is that this 5 plays an important role. Uh, this 5 plays an important role in finding the response in determining the response for the system. So this system, which has a transfer function equal to S plus 2 divided by S plus 5, right? This 5 plays an important role in determining the natural response for the system, and this 2 actually determines the amplitude of of the forced response and the amplitude of the uh, natural response. So the denominator, the term in the denominator determines the nature of the natural response. It is an exponential term with a decaying uh, part equal to e to the power minus 5t, and the numerator part determines the magnitude of the response, right? The this 2 that you have here, and this, in fact, this 3 that you have here, this 2 has a role in determining the magnitude of the response. So in addition to the fact that this part is because of the input and this big part is because of the nature of the system. So we have specific names to these terms that that are there in the numerator and denominator. So any number, any value of s, value of s, that makes gs equal to 0, right? Like 2 here is called the 0 of gs. So a 0 of gs makes gs equal to 0 at that point. So we have a 0 here, which is given by s is equal to -2. Similarly, value of the complex variable s, value of s that makes gs equal to infinity is called the pole of gs. It's called the pole of gs. So the pole of gs is here, is equal to -5, right? So the pole determines the nature, and the 0 determines the magnitude of the natural response, right? So you can basically represent the poles and the zeros on a plane called the S-plane. S-plane, because S is a complex variable, so it is represented on the S-plane with a real axis, the x-axis as the sigma or the real axis, and the y-axis as the imaginary axis. So S is equal to sigma plus j omega, with sigma sketched along the x-axis and j omega sketched along the y-axis. So in this case, you have a 0 at s is equal to -2. So at s is equal to -2, you have a 0, and at s is equal to -5, right? So that would be somewhere here. S is equal to -5. You have a pole. A pole is represented as a cross normally on the s-plane, and a 0 is represented as a 0 on the s-plane. So this is called the pole zero plot. Pole zero plot of the transfer function that we are trying to see, right? So why is this important? Because immediately, without even solving for the transfer function and the response, we would know what are the terms going to be in the response, right? So for example, you have something like a divided by s plus 1, s plus 2, s plus 3, right? Where a is some constant, right? And you are subjecting this system to a step input, right? So you are giving it rs is equal to 1, so 1 by s. So without even solving for this completely and finding the Laplace inverse, you can say that the response is going to contain terms e to the power minus t because of this, e to the power minus 2t because of this, e to the power minus 3t because of t, this, and there would be some constant term because of the input that is there, so some constant k. So you'll know that the overall response will be the sum of these these four responses, right? So this was just a small introduction about this. Now let us actually talk about the different types of systems and their transfer functions. So the first type of systems that we encounter are the first order systems, right? As I've said before, order basically represents the degree of the denominator of the transfer function. Denominator polynomial, right? Which is a polynomial in S. So degree of the denominator polynomial of the transfer function. This is the order of the system, right? So if the degree of the denominator polynomial is 1, it will be a first order system. So a first order system would in general be something like this. If it has just a pole, it will be a, for example, a divided by s plus a. So this is a typical first order system. And if you subject it to a step input 1 by s, you'll get a divided by s into s plus a, and you can take the inverse of this ct. That is going to be, if you open this up, you'll write this as a by this as 1 by s minus 1 divided by s plus a, right? This would be opened up like this. This is your CS, and then you can write down your CT as 1 minus e to the power minus at. So this is the response. This is a typical first order response. If you sketch this response, C of t versus t, e to the power minus at is going to be, if you sketch just this much, it is going to start at 1 and then decay to 0, because at t e to the power minus at, at t is equal to 0, e to the power minus at is 1, right? And then it is going to decay to 0 depending upon what is a. So e to the power minus at is going to be something like this, right? And we are not interested in e to the power minus at, we are interested in 1 minus e to the power minus at. So if you want to subtract, if you subtract it from 1, right, you will get 1 minus e to the power minus at, which is going to be something like this. So this is the response. This is the response of the first order system, a divided by s plus a, when you subject it to the step input. Now we are going to characterize this response, right? What is the speciality? Can we give it some? Can we define it properly? You can very easily see that if you're able to characterize it using a, you're basically characterizing the response completely, right? Now what is a? Let us look at the term e to the power minus at, which is how it is decaying. So if I say what is the value of e to the power minus at when t is equal to 1 by a, right? When t is equal to 1 by a, e to the power minus at is equal to e to the power minus 1 is equal to 0.37, right? So the exponential part, the decaying part, or the natural response, right, has started from 1, the natural response. This red is natural response, right? And 1 is the forced response in green, and black is the total response, right? So the natural response started from 1, and at t is equal to 1 by a, it reduced to 0.37, right? So this is called the time constant of the response. Time constant, to define it, would be, from this definition, would be the time for during which e to the power minus at, the time during which the natural response which is e to the power minus at, decays to 37% of its initial value. Initial value is 1 and it becomes 0.37, which is 37% of its initial value. Or the other definition would be the time during which the total response, right, reaches 63% of its steady state value, right? The steady state value is the value of the response when it stabilizes, right? So when it stabilizes, the value becomes 1. And what is the value at t is equal to 1 by a? At t is equal to 1 by a, c of t is equal to 1 minus e to the power minus at, right, which is equal to 1 minus e to the power minus 1, which is equal to 1 minus 0.37, which is equal to 0.63. So at t is equal to 1 by a, the value has reached 63% of its steady state value. So these are two definitions of the time constant, right?